Okay, so in this part, I'm going to discuss the completeness property for RK, which remember, so when I refer to RK as a metric space with no further explanations, the default assumption is that I'm talking about Euclidean space, right? So we're using the Euclidean metric on RK, which is the formula with the square root and the sum of the squares of the differences, yada yada, that you get from the Pythagorean theorem, right? So in order to, we would like to show that RK is complete, okay? To get there, I'm going to show the lemma, what they call lemma 13.3, okay, which has to do with the, so it has to do, well, okay, before I write it down, the lemma has to do with the, what you can say about convergence, sort of a basic fact about convergence of sequences of points in RK. And it has to do with about like saying that when a sequence of points converges, it's the same thing as like each of the coordinate sequences converging. So this is a little bit complicated. It's a little bit hard to think about because there's a lot of subscripts flying around. So let me just sort of familiarize you with the basics of the notation. In this context, they like to talk about the points, the way they write the points in the sequence, right? We have a sequence of points in RK. So consider a sequence of points in RK. We use the notation in this context, at least. Okay, it is valid to say something like, xn. You can write that, and it'll be like xn will just be the nth point in the sequence, right? So that point will have k coordinates, k components in it, right? You could also call it a vector if you want. But because we want to also talk about like the different components of each one, for the sequence, we actually use the instead of using like a subscript, we actually use a superscript. So the notation will be like this. We'll have x and superscript in parentheses, where this means, so the sequence looks like this, okay? So looks like this. We'll have x1, x2, right? x3. And I'm actually going to be dropping these vector signs. Actually, no, I'll try to write them just to keep things super clear. So on, right? And then we have xn, so on. This is the sequence xn, right? Now, each of these points is a list of numbers, right? So we have x, and instead, I'm not going to put vectors on these. Yeah, okay. So we'll have x1, 1, x1, 2, x1, 3, up to x1, k, and that's it, right? Because we're in k space. And then here we'll have x2, 1, x2, 2, x2, 3, x2, k, right? x3, 1, x3, 2, x3, 3, x3, k. And in general, we'll have the nth point will have coordinates x, xn, 1, xn, oops, n 2, xn 3, xn k. So that's basically what the sequence looks like. And now I'm just going to kind of describe what theorem or lemma 13.3 says. So I'll write it down here. Or yeah, I'll show you what I mean down here. So let me erase this a little bit. Switch colors. So lemma 13.3 says that this sequence, sorry, so this sequence here converges if and only if this sequence converges and this sequence converges and this sequence converges and so on. So every one of these sequences has to converge. Okay, so these, remember, these are sequences of numbers in R itself, right? So these are just normal sequences of numbers like what we've seen before. And this here is a sequence of points in RK. So the definitions of convergence are slightly different for these different sequences, okay? So what we're gonna show is that this overall sequence of points converges if and only if each of these coordinate sequences, these are what I call the coordinate sequences, okay? This is the first coordinate sequence, this is the second coordinate sequence, and so on. Each coordinate sequence has to converge, and actually, moreover, that the limiting point of the overall sequence, the coordinates of that point will be the limits of each coordinate sequence listed off, right? So you'll take the limit of this sequence, the limit of this sequence, and so on to get the overall limit here. This is actually the lemma that we want to show. So let me make a new page here. Okay, let's, sorry, my phone started ringing in the middle of that, so I had to cut. So let's talk about the proof of lemma 13.3, and I don't want to go through it in too much detail. I just want to show you kind of the main important strokes, the main insights here, okay? So let's think about it. So let's state 13.3. Well, actually, it's a few things. So, oops. So lemma 13.3, oops. The first statement is, so I actually didn't fully state it in the previous bit, but the first statement is that, so basically xn converges in RK if and only if each xj, or maybe xj and converges in R. And of course, then, moreover, that when they both converge, the limit of this sequence of points is the point whose coordinates are the limits of these sequences, right? So that's the first thing. But then there's a second one, which is this statement about Cochise sequences. And that's actually the one that we're going to prove. The first one is actually an exercise. So we're going to prove the second sequence here. Although I don't think I assigned this as an exercise, but yeah, I just don't have time to go through it. And it's actually pretty much the same argument anyway. So, okay, and then the second one is xn is Cauchy in RK if and only if each xj n is Cauchy in R. Okay, so let's talk about the proof. Let's talk about the forward direction, okay, of the second part here. So of 2, let's call this one 2, right? So the proof of 2, moving forward. So suppose xn is Cauchy, right? So we can bound the distance of xn and xm above by epsilon, right? So we want to force, what we want to show, sort of, quote unquote, is that we can bound these numbers above by epsilon as well. So for each j, right? Specifically for j between 1 and k, right? Right. So there are k different sequences here since we're in RK, right? So there's one for each value of j, and then we let the upper subscript move around to form that sequence, right? Or the superscript here. So the way you do this is actually very simple. You can just say xj minus xjn minus xjm is less than or equal to the square root of, x1 n minus x1 m squared plus xk minus xk n m squared, right? So why is this the case? That's because, well, actually, maybe it would be better to do this. Let me expand on this a little bit. So xj n minus xj m is equal to the square root of xj n minus xj m squared, which is less than or equal to this, right? Oops. So if you see, right, this expression is less than or equal to this one just because in going from here to here, we just added, right, this term xjn minus xjm is in here somewhere, right? And then we just like added a bunch of other positive terms in here, so that has to make the expression bigger, okay? So if this is less than or equal to this, so the same capital N value, so if we choose capital N such that the distance of, remember, this is the distance of x n and xm. So if we choose capital N such that this distance is less than epsilon, then, so for all n greater than n, right? Then the distance xjn minus xjm is less than or equal to epsilon for n greater than n as well. So that one's actually fairly straightforward. Now let's, I'm gonna erase this and we'll talk about the reverse direction, which is only slightly trickier. Okay, so now we want to prove the reverse direction here, which is where we assume that each coordinate sequence is Cauchy, and then show that the overall sequence is also Cauchy, which is basically, right, we want to bound the distance from xn to xm in terms of the numbers xj n minus xj m for each j. Okay, this is generally what we're trying to do. So basically it's like what we have control over is these quantities, right, for each j, because we're assuming that these sequences are Cauchy. We can make these small by forcing n and m to be big enough, right? And we can do that for every j, okay? So we want to sort of look at the relationship between these two and say there's some expression involving these numbers which is actually bigger than this one, and that way by making this expression small in terms of these numbers, we'll end up making this one small, which is our goal, right? So here's the relationship, okay? We see that, so we have this x1 minus x1 n m squared plus xk minus xk n m squared is less than or equal to the square root of, now we use the maximum, right, of these xj minus xj n m squared. So the maximum over the j's, right? So j equals 1 up to k. So if you maximize this number over j and then just replace each of these by that, right? So it's the same thing. Plus, right? So if we just replace each of these terms by the maximum of all of the terms, then the expression has to get bigger, right? But when we do that, you just end up with k times the maximum inside, right? So I'm gonna erase, so it's just, I'm just replacing each term here with a copy of the maximum of all of the terms, right? So I'm gonna erase these because it's too much writing. And what we end up with is a square root of k times the maximum of those terms, right? So then this equals square root of k times the maximum of the absolute value, right, of xj n minus xj m for j equals 1 up to k, right? And so this is just, right, now this is actually written directly in terms of these numbers. So basically by forcing these numbers to be smaller than, you know, something related to epsilon, so it'll be something like epsilon over over square root of k or something, then we'll make this thing be less than epsilon, right? So choose, so I'll just say this, choose n such that x j n minus x j m is less than epsilon over square root of k for all j, you know, for j, let's say, you know, for j equals 1 k for all n and m greater than capital N. And we can do this because we can choose a capital N for each one of these values of j separately, and then we can just take the biggest capital N out of all of those, right? So we can basically make this entire, we can make all of these be less than epsilon over square root of k. That will force this to be less than epsilon, and that in turn forces this to be less than epsilon for all n and m bigger than n, which is what we want, right? So I know it's a little bit complicated, but there's actually some good techniques in here about estimation and proofs of, you know, convergence or the Cauchy criterion for sequences. So hopefully you learned a bit. And in the next video, we'll talk more about completeness.